Alright, welcome back guys. This is the third part of transport phenomena under the diffusivity of a gas mixture. So today we are going to take a look at the third part. So let me read the question again. The question states, estimate the diffusivity AB for carbon dioxide and nitrogen at 273.2 Kelvin and 1 atm. A, using Slattery equation. We have done this in part A. B, using Chapman Enskog formula for an ideal situation. You have done this in part B. So C, if the gas pairs of of carbon dioxide to nitrogen were to be at 150 degree Fahrenheit and 1470 psi, what would be the diffusivity AB using the value obtained from A? That is value obtained from Slattery equation, right? So, and the fact that it is an equimolar. So this is the part we are going to take a look at now, part C. So here is the question. So since they mentioned that the fact that it is an equimolar mixture, that means what the mole fraction are equal. So let's start. Please subscribe, like, and share. Thanks. So the first thing we are going to do is to convert the given temperature and pressure. So, and how do we do that? From the question, we are given what? Temperature in degree Fahrenheit, which is what? Temperature equal to 150 degree Fahrenheit. So to convert it to Kelvin, we are going to make use of this formula. That is temperature in Kelvin is equal to degree Fahrenheit minus 32 divided by 1.8 plus 273. So substitute the value of temperature in degree Fahrenheit. You have, that is, in degree Fahrenheit, you have it as 150 degree Fahrenheit, 150 minus 32 divided by 1.8 plus what? 273. We have it as 338.6 Kelvin. So the second is convert the pressure. We are given pressure from the question. Pressure equal to 1470 psi. So we have to convert it to atm because that is the SI unit you are making use of. So to convert it to atm, if you check your conversion table, the conversion factor between atm and psi is 1 atm will give us 14.7 psi. So we need to convert this 1470 psi to what? atm. Now what we are going to do is 1470 psi multiplied by 1 atm. So this is the logic. Since psi is at the numerator, it's not inverse. So you make sure that the conversion factor, which entails what? psi, should be at the denominator so that it can cancel. So that is multiplied by what? 1 atm divided by this, that is 14.7 psi. So at the end of the day, we can see that this psi cancel this psi. So equal to 1470 multiplied by 1. That is still the same as 1470 divided by what? 14.7. You have it as 100 atm. Alright. So the next thing is to determine the diffusivity at what? As 338.6 Kelvin at 100 atm. What you are going to do is what? Standardize the diffusivity from example A. Let's label it as diffusivity AB1 is 0.133 centimeter square per second. If you check part A, you will find it that the answer we got in Slattery equation, that is in A example A is 0.133 centimeter square per second. So this is the initial diffusivity we are going to make use of. That is from example A. So what we are going to do is to standardize diffusivity AB at what? At 150 degree Fahrenheit. That is at what? 338.6 Kelvin. And to do this, we are going to make use of oscillatory equation. That is using Slattery equation. So, mind you, we label the diffusivity gotten from what? Example A, sorry, as 0.133. So, let's label the diffusivity that we are standardizing at this temperature, that is 338.6 Kelvin. So, let's label it as diffusivity AB2. So, in this case, using Slattery equation, you know that diffusivity AB1 will be what? A multiplied by B multiplied by C multiplied by what? D, all divided by P. The same thing as what? Diffusivity AB2, that is the one we are standardizing to. We have it as A multiplied by B multiplied by C multiplied by D, all divided by P. Label this as equation 1 and label this as equation 2. So in this case, divide equation 2 by equation 1. So that is diffusivity AB2 divided by what? Diffusivity AB1 equal to. So now, diffusivity AB2, that's what? A multiplied by B multiplied by C multiplied by D, all divided by P. And diffusivity AB1 is what? A multiplied by B multiplied by C multiplied by D, all divided by what? C. So this is the logic. We don't need to write everything. We know that from the previous part, that is from the previous example, A has the formula of PCA. That is, A has the formula that contains only what? Critical pressure. So, and we know that the critical pressure is the same since we are still making use of what? Of the same mixture. So that means A we cancel out. That means A we cancel out. So the same thing happens to B. You know that the formula for B involve what? Critical temperature. So since we are still making use of the same mixture, so their critical temperature will be the same. So that means B will also cancel out. So the same thing happened to what? C, because C involve what? Formula of what? Molar mass. It involves molar mass on the formula. So since we are still making use of the same mixture, they are the same, they will cancel out. Okay. But okay, before coming to D, let's see P. Mind you, we are standardizing at what? This temperature, 150 degree Fahrenheit or what? Which is the same thing as 338.6 Kelvin. So since we are considering temperature, not pressure, so that means we are still going to make use of what? Pressure from what? Example 1, that is what? 1 atm. The pressure will cancel out because they are the same. So in this case, we are left with what? We are left with D. So mind you, D has a formula of what? A into bracket actual temperature over square root of what? TCA multiplied by TCB, or raised to power of B. Alright. So in this case, for diffusivity AB1, it has this actual temperature as what? As 273.2. The first temperature in which we got this diffusivity 1 has what? Corresponding temperature of 273.2 Kelvin. So, and for this, we are standardizing at what? At 150 degree Fahrenheit or what? 338.6 Kelvin. So that means the temperature and the actual temperature are not the same. So in this case, it can cancel out. What we are going to consider is what is, that A is a constant and B is also a constant. Okay, let's divide it. So we have it as A into bracket actual temperature of 2. Let's label it at 2. That is 338.6 is the actual temperature of the second diversity you are standardizing to. So divided by, let's label this square root of TCA multiplied by what? TCB as what? Delta. Alright. Or is power of B divided by A into bracket actual temperature of 1, that is of this diffusivity, which is T1, divided by labeling this as delta also. Or is power of B. This A, since they are both constant, they can cancel out. So this delta, since they are the same thing, because the critical temperature are the same, since you are dealing with the same mixture, they will cancel out. So we will be left with what? T2 over T1. Or is power of, they will share the same power. Since they are the same power, they have the same power, they will share only one. That is RS power of B. So in this case, we have T2 as the temperature we converted, which is 338.6 Kelvin. Right? I have T1, that is the initial temperature from the question, 273.2 Kelvin. So, and we know that we have diffusivity A, B1 as well, 0.133 centimeters square per second. So we are going to standardize this diffusivity at what? At this temperature now. So making use of this Slattery equation formula, we have what? Diffusivity AB2 over diffusivity AB1 equal to T2 over T1, right? Or is power of what? B. So mind you, B is a constant as what? 1.823. You understand? So substitute the value in, we can see that we'll be having diffusivity AB2, that is what we are looking for, over what? Diffusivity AB1, that is what? The initial what? Diffusivity from example 1, 0.133, equal to T2, which is what? The temperature that we are standardizing to, which is 338.6, divided by T1, that is initial temperature, 273.2. All raised power of what? B, which is what? 1.823. With this, we know that this division will be what? 1.479. Cross multiply, we have diffusivity AB2 equal to what? This multiplied by this. That is 0.133 multiplied by what? 1.479. So we have it as 0.197 centimeters square per second. This is the value for standardizing at the given temperature, that is 338.6 Kelvin. So, and mind you, this is not our final answer. So where we are going to find our final answer is to standardize it again at 100 ATM. Actually, To standardize it using the temperature is the first step. So the second step is to standardize it using the what? The pressure given. So and the pressure given is 100 atm, that is 1470 psi. So in this case, this is where the generalized chart for self-diffusivity is coming. So this generalized chart for the self-diffusivity is what is a plotting of what pressure and diffusivity against what reduced temperature and reduced pressure. That is, generalized chart for self-diffusivity is given as P diffusivity AB divided by P naught diffusivity AB naught is plotted against PR and TR. So where PR is the reduced pressure and TR is the reduced temperature. So this is the actual pressure, the second actual pressure in which we are standardizing to using generalized chart for self-diffusivity. So this is the diffusivity we are looking for actually. So this initial pressure from example 1, and this is what the initial diffusivity we got from what we got while standardizing at what the second temperature, which is 0.197 centimeters square per second. So let me break everything down. We have reduced pressure as what? Actual pressure over critical pressure. And you have reduced temperature as actual temperature over what? Critical temperature. So in this case, since it is a mixture, we can't just conclude that, or we can't just add their individual critical temperature or critical pressure and use it for either critical temperature or critical pressure. That is not how it works. So for the critical pressure, we make use of this formula: summation of mole fraction of individual gases multiplied by critical pressure of individual gases, which is what? Mole fraction of A multiplied by critical pressure of A plus mole fraction of B multiplied by critical pressure of B. So the same thing happens to what? Critical temperature. Since it is a mixture, we have summation of xi, that is mole fraction of individual gases, multiplied by critical pressure of individual gases, which is the same thing as xa multiplied by tca plus xb multiplied by tcb. So you can go back to your critical table. Let's use this table as gas, critical pressure, and what? Critical temperature. So under gas, we can have what? We can have A, that is for carbon dioxide, and I have B, which is for what? Nitrogen. Check this table overlay. We have our critical pressure for carbon dioxide as 72.8, and the critical pressure for nitrogen is 33.5. Now, the critical temperature for carbon dioxide is what? 304.2 Kelvin, and the critical temperature for nitrogen is 126.2 Kelvin. So after getting this, we are going to substitute everything to this formula respectively to get the corresponding PC and what TC of the mixture. So from the question, it mentions that what the fact that it is an what equimolar mixture. I asked you to take note. Then, so since it is an equimolar mixture, that means their mole fraction are what equal, and the total mole fraction of a mixture must be equal to 1. That is the total mole fraction. That is equal to mole fraction. You can also call it mole ratio. Either mole fraction or mole ratio. So, and the total mole fraction or mole ratio in a mixture must be equal to 1. All right. So in this case, since they are equimolar and we have two elements in the mixture, right? So that means each will be what 0.5. That means what XA equal to 0.5 and what XB equal to 0.5. All right. So we can now substitute into the given formula. We have PC equal to what XA multiply PCA plus XB multiply PCB, which is equal to what XA 0.5 multiplied by PCA, which is critical pressure of what carbon dioxide 72.8 plus 0.5, which is XB multiplied by critical what pressure of nitrogen 33.5. So in this case, we have it as 53.15 ATM. Yeah. So we can also apply the same scheme towards the critical temperature, which is XA TCA plus XB TCB equal to XA is what 0.5 multiplied by TCA, which is what 304.2 plus XB, which is 0.5 multiplied by TCB, which is 126.2. We also have this as 215.2 Kelvin. So the next thing we are going to calculate is the reduced temperature and reduced pressure. So since the reduced pressure is what the actual pressure over the critical pressure, right? And we have actual pressure as what 100 atm divided by what the critical pressure of the mixture, that is 53.15 atm. So in this case, we have it as 1.9, right? So secondly, in terms of reduced temperature, we have it as actual temperature over critical temperature, right? Which is equal to the actual temperature, that is the temperature we converted from the beginning, which is 338.6 Kelvin divided by the critical temperature of the mixture, which is 215.2. We also have this as 1.6. So with this value, we are going to make use of a chart called Generalized chart for self-diffusivity. It's still part of transport phenomenal property table. So, and it is called Generalized chart for self-diffusivity. So checking this chart, you can see the vertical column as for diffusivity and the horizontal column as for what? Reduced pressure. You can see P out there, reduced pressure. So, and the curves are for reduced temperature. So under the curve, we can see curve of 0.9, curve of 1.0, 1.1, 1.2, 1.3, up to 3.5. Yeah. And under the reduced temperature, the horizontal, the reduced pressure, sorry, you can see it from 0 towards 6.0. And at the vertical, that's for diffusivity, we have from 0 towards 1, that at the range of 0.2. So in this case, we are going to check the reduced temperature and pressure in this chart, and we'll find the value for what diffusivity. So that is how we are standardizing at this level, at this what pressure of 100 watt atm. So we have reduced pressure as what 1.9. Check it. Is there any 1.9 in the horizontal as this, which is for reduced pressure? No, but it's between what 1 and what 2. Okay, let's say it's very close to what 2.0, right? So let's point at this place. So at reduced temperature, we have it as what 1.6, right? This 1.6, check the curves. The curve is meant for what? Reduced temperature. So we have 1.6 here. So just try to check it. So try to intersect the line that's from horizontal as this, which we have 1.9. So intersect it to this curve of what 1.6. So after intersecting it, just imagine where they meet and what you can even use a ruler. So trace it to what, to the left, that is to the what diversity side. So under this diversity line, you can see it as 0.89. Yeah, 0.89. So the value might not be the same. You might make use of 0.88 or 0.89 or 0.9 because the way we are seeing things or the way we are viewing things are not the same. So everything is still correct. The range won't be much, but make sure what you're doing is accurate. Do it as your best. So here we have it as what 0.89. I'm using 0.89. So that means P diffusivity AB divided by P naught diffusivity AB naught against reduced pressure and what reduced temperature is equal to 0.89. So in this case, let's substitute the value in. We have P, this outer pressure as what 100 atm, multiplied by what diffusivity AB, because this diffusivity you are looking for, divided by P naught, which is what the outer temperature from what from the beginning, that is from example 1, which is 1 atm, multiplied by diffusivity naught, which is what standardized diffusivity we got from using temperature, which is 0.197, right? Equal to what? This 0.89. So in this case, we can have the diffusivity AB as what? 0.00175 centimeter square per second. Or you can put it in standard form, which is what? 1.75 times 10 to the power of minus 3 centimeter square per second. So this is the estimated diffusivity for the gas pair of carbon dioxide to nitrogen at pressure of 1470 psia, which is also 100 atm, and a temperature of 150 degrees Fahrenheit, which is also 338.6 Kelvin. So this is the estimated temperature. So mind you, for the first one, for Slattery equation and Chapman Enskog formula for an ideal situation, they are used for low density mixtures, that is pressure at 1 atm or close to 1 atm. But at high density or at high pressure, we make use of what? Generalized chart for self-diffusivity. And don't forget to like, share, and subscribe. This is the end to this part. Thank you so much, guys.